Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. A fortress wall, to be effective in the age of artillery, required a peculiar sort of invisibility. Its purpose was concealment from the arcing trajectories of cannonballs, a problem of three-dimensional geometry played out with stone, earth, and human lives. This challenge, known to the French Corps of Royal Engineers as the problème du défilement, or the problem of défilade, obsessed military strategists of the 18th century. The goal was absolute: to design fortifications, ramparts and trenches so that every single point of the defensive works remained shielded from enemy fire, regardless of the topography or the placement of hostile batteries. A failure in this geometric calculus meant a breach, and a breach meant catastrophe. Before the late 1700s, solving this problem was a grueling, imprecise affair. It relied on cumbersome physical models, mountains of arithmetic calculations based on rough approximations, and the guarded, almost mystical trade secrets of master builders. The world of practical construction and the world of pure geometry existed in separate, barely interacting spheres. The art of building, particularly the sophisticated craft of stereotomy, the cutting of stone for complex structures like vaults and spiral staircases, possessed a deep yet unwritten geometric wisdom. Its practitioners worked with empirical rules and graphical shortcuts, passed down through generations. These methods worked, often beautifully, but they were idiosyncratic, difficult to teach, and impossible to generalize into a coherent scientific system. An engineer facing a novel fortification challenge on uneven ground was essentially starting from scratch, armed with little more than intuition and laborious arithmetic. What was desperately needed was a universal language, a rigorous and systematic method for translating the solid, three-dimensional reality of a fortress or a bridge into a two-dimensional representation that preserved all essential spatial information. A system was required that could allow an engineer to see through the stone, to predict the intersection of unseen surfaces, and to determine the true shape of a complex cut, all on the surface of a drawing board. This was the world inherited by Gaspard Monge, a brilliant young man of humble origins, who through sheer talent secured a position as a draftsman at the prestigious Royal School of Military Engineering in Mézières. His initial duties were far from glorious. He was tasked with the tedious arithmetic required to map out a proposed fortification plan. Confronted with endless columns of figures, Monge felt a profound intellectual impatience. The existing process struck him as inefficient, an opaque numerical slog to arrive at a visual spatial solution. He was convinced a purely geometric approach would yield the answers with superior speed and clarity. In a stroke of insight that would reshape the physical world, he developed one. His solution, which he would later codify under the name geometry descriptive or descriptive geometry, was an act of profound intellectual organization. Monge conceived of space as being defined by two imaginary infinite planes, intersecting at a right angle. One plane was horizontal, the plan views; the other was vertical, the elevation views. Any object in space could be projected orthogonally, meaning at a right angle, onto each of these planes. The resulting pair of two-dimensional drawings, the plan and the elevation, formed a complete and unambiguous representation of the three-dimensional object. The genius of the system lay in the fixed relationship between these two views. By rotating the horizontal plane down until it was coplanar with the vertical one, Monge could place both views on a single sheet of paper, linked by projection lines. This simple, elegant construction was a key that unlocked a universe of practical problems. From this pair of drawings, an engineer could now perform a series of straightforward graphical operations to find the true length of any line in space, a task crucial for cutting beams or planning lines of sight. One could determine the precise angle between two intersecting planes, essential for designing stable ramparts or perfectly fitting stonework. Most powerfully, one could find the exact line of intersection between two complex surfaces, like a cylinder piercing a cone, a core problem in everything from cannon placement to vault construction. Monge's method replaced laborious calculation and empirical guesswork with a precise visual and logical procedure. It transformed a craft into a science. So potent was this new technique that his superiors at Mézières, recognizing its immense military advantage, classified it as a state secret for nearly 15 years, a rare instance of a mathematical proof being treated as a strategic weapon. The applications of descriptive geometry radiated far beyond the battlefield. Monge's system provided the first true scientific foundation for stereotomy. The complex, three-dimensional thinking required to envision how the curved surfaces of an arch or a dome would be formed from flat-faced blocks of stone could now be externalized and perfected on paper. The master mason could lay out the exact shape, or templates, for each unique stone with complete confidence. This innovation democratized advanced construction, reducing material waste, improving structural soundness, and allowing for architectural forms of ever-increasing complexity. It was a revolution in how humanity built its world, a bridge between the abstract realm of Euclidean solids and the tangible reality of wood, stone, and steel. The conceptual leap Monge initiated was immense. He provided the intellectual toolkit for the Industrial Revolution, establishing the visual language of the engineer and the architect. Every technical blueprint produced in the 19th and 20th centuries, every schematic for a steam engine, a skyscraper, or an airplane, is a direct descendant of Monge's system of plan and elevation. The fundamental logic of modern computer-aided design, or CAD, software, which allows engineers to model and analyze complex three-dimensional objects on a two-dimensional screen, is a digital apotheosis of the principles first laid down at Mézières. He had found a way to perfectly capture static, three-dimensional form on a flat plane. Having achieved this, Monge's powerful intellect began to probe deeper, turning from the representation of surfaces to the intrinsic, dynamic properties of the surfaces themselves, exploring the very fabric of form through the language of calculus. The analytical power of the calculus, which had so masterfully tamed the behavior of curves in the plane, presented a far more formidable challenge when applied to the three-dimensional world. For the generation following Newton and Leibniz, a curve was a well-understood entity. Its slope at any point could be found with a derivative, the area beneath it with an integral. A surface, however, was an infinitely more complex beast. Its steepness, its very curvature, changes with every infinitesimal turn of perspective. The shortest path between 2 points on its face is rarely a straight line. The central intellectual problem of the late 18th century was how to extend the rigorous language of analysis to these fluid multidimensional forms. It was here, in the domain we now call differential geometry, that Gaspard Monge established himself as a founding father, moving from the task of drawing surfaces to the profound challenge of understanding their intrinsic soul. His first great conceptual advance was to wield the partial differential equation as a generative tool. Previously, an equation described a single, specific curve or surface. Monge envisioned something grander. He saw that a partial differential equation, an equation involving rates of change with respect to multiple variables, could define an entire family of surfaces bound by a common geometric property. For example, one could write a single equation whose solutions represented every possible sphere of a given radius in three-dimensional space. To find a specific surface that satisfied additional constraints, such as passing through a particular curve in space, one had to solve this differential equation. This reframed the entire discipline. Geometry became a dynamic process of generation and constraint, governed by the laws of calculus. He created a dictionary for translating geometric properties into the language of analysis, and for translating analytical solutions back into geometric forms. With this powerful new language, Monge began to dissect the very nature of curvature on a surface. He posed a fundamental question: at any given point on a surface, say the side of a hill, in which direction is the slope steepest, and in which is it the most gentle? He demonstrated that these two directions are always perpendicular to each other. By tracing these paths of maximum and minimum curvature across the entire surface, he conceived of what he termed lignes de courbure, or lines of curvature. These lines form a natural intrinsic grid on any smooth surface, an orthogonal mesh woven into its very fabric. Imagine the lines of longitude and latitude on a globe. Monge's insight was to show that every surface, no matter how complexly twisted or undulating, possesses its own inherent system of coordinates defined by its own curvature. This gave mathematicians a canonical way to orient themselves at any point on a surface, providing a framework to analyze its properties independent of how it was situated in ambient space. This deep investigation into the structure of surfaces yielded results of immense practical utility. Monge undertook a systematic study of a special class he named developable surfaces. These are surfaces like a cylinder or a cone that can be unrolled onto a flat plane without any stretching, tearing, or distortion. He provided the definitive analytical criterion for identifying them. A surface is developable if it is composed of a sequence of straight lines and can be formed by the tangent lines to a curve in space. The insight was profound. He showed that the ability to be flattened is an intrinsic geometric property, one that could be detected with calculus. This discovery had immediate and far-reaching consequences for industry and engineering. The ability to calculate the precise two-dimensional shape needed to form a three-dimensional object, be it a curved section of a ship's hull, a conical piece for a steam boiler, or a complex elbow joint for a pipe, was a direct application of this theory. It allowed for the efficient and exact fabrication of complex parts from flat sheets of metal, a cornerstone of the burgeoning Industrial Revolution. His analytical explorations continued, leading him to formalize the theory of envelopes. The concept is best visualized by imagining an expanding family of spheres, perhaps originating from every point along a curve. The envelope is the new surface that is formed by being tangent to every single one of these spheres. Monge developed the partial differential equation machinery required to find the precise form of this envelope for any given family of surfaces. This work provided a powerful method for generating complex new shapes from simpler ones, revealing deep connections between different geometric forms. It was a testament to his unique genius, a mind that could simultaneously perceive the grand, intuitive geometric picture and command the intricate analytical formalism needed to give it rigorous expression. Through these investigations, Monge laid the complete analytical foundation for the great flowering of geometry in the 19th century. His work on lines of curvature and developable surfaces directly anticipated the more general and abstract theories of intrinsic curvature that would be perfected by Carl Friedrich Gauss. His methods of using partial differential equations to study families of surfaces would be the essential starting point for the higher dimensional explorations of Bernhard Riemann. The concepts he pioneered are now fundamental to fields as diverse as computer-aided design, where they allow for the seamless modeling of complex objects, and modern physics, where the curvature of space-time itself is described using a mathematical language that is a direct intellectual descendant of Monge's initial inquiries. This same mind, so adept at discerning the hidden order within abstract mathematical forms, would soon be called upon to impose a new rational order upon the chaotic political and social structures of a nation in upheaval. The intellectual framework that allowed Gaspard Monge to perceive the underlying geometry of physical space was perfectly suited for the immense task of national reconstruction. The French Revolution, in its ambition to sweep away the ancient regime, created a vacuum demanding new structures built upon foundations of reason and scientific principle. For Monge, the unfolding political drama was a grand, practical problem, an opportunity to apply his geometric imagination to the very architecture of the state. His fervent republicanism was inseparable from his scientific rationalism. He saw in the revolution a chance to redesign a society with the same elegance and logical coherence he sought in his mathematical proofs. This profound alignment of personal conviction and historical moment propelled him from the quiet halls of the academy into the turbulent center of French political life. His first major foray into statecraft came with his appointment as Minister of the Marine in 1792. The young republic was embattled, its survival dependent upon its military prowess. The French Navy and its associated industries, however, were relics of a bygone era, plagued by inefficiency and archaic practices. The production of cannons, in particular, was a critical bottleneck. Monge approached this challenge with the systematic mind of a geometer and the practical knowledge of a metallurgist. He embarked on an exhaustive tour of the nation's foundries, observing, analyzing, and documenting every stage of the manufacturing process. He applied his deep understanding of chemistry to improve the quality of iron and steel, and rationalized the techniques for casting and boring cannon barrels. He transformed what had been a craft based on inherited, often secretive traditions into a standardized industrial science. Through his efforts, the foundries of the Republic became a formidable engine of war, producing munitions with unprecedented speed and reliability, arming the revolutionary armies that would soon march across Europe. This drive to impose rational order extended to the most fundamental elements of civic and commercial life. Pre-revolutionary France was a bewildering tapestry of weights and measures, with hundreds of local, incompatible systems that hampered trade, confused taxation, and created a persistent barrier to national unity. The system was a daily reminder of feudal fragmentation. As a leading member of the commission tasked with creating a new universal standard, Monge became a principal evangelist for the metric system. The project was the Enlightenment ideal made manifest, a system of measurement derived from nature itself, specifically from a quadrant of the Earth's meridian. His expertise in geodesy was essential to the monumental survey required to measure the arc from Dunkirk to Barcelona, the physical measurement that would define the meter. This was geometry in service of the people, an attempt to create a language of quantity that was universal, decimal, and accessible to all citizens. The meter, the gram, and the liter were to be the new vocabulary of a rational and unified nation. Yet, his most enduring contribution to the structure of the modern state was an institution. The revolution had swept away the old universities, leaving the Republic without a system for training the next generation of scientific and technical leaders. To fill this void, Monge became the chief architect of what would become his pedagogical masterpiece, the École Polytechnique. Founded in 1794, this new school embodied his entire worldview. He designed a curriculum that fused the highest levels of theoretical science, especially mathematics, with rigorous, hands-on practical application. He placed his own descriptive geometry at the very heart of this new educational model. For Monge, this was the essential skill. It trained the mind to visualize and manipulate complex three-dimensional forms, to translate abstract mathematical ideas into concrete plans for bridges, fortifications, machines, and public works. Students at the École Polytechnique learned a new way of thinking, a visual and analytical language that empowered them to design the very infrastructure of a modern industrial nation. The school became a template for elite technical education across the world, a testament to Monge's vision of a scientific core dedicated to the service of the state. His influence and reputation reached their zenith under the patronage of his most famous admirer, Napoleon Bonaparte. When Napoleon launched his ambitious expedition to Egypt in 1798, it was conceived as a military conquest and a grand scientific endeavor. He selected Monge to lead the prestigious Commission des Sciences et des Arts, a corps of over 160 civilian scholars, engineers and artists tasked with conducting a comprehensive survey of Egypt. In the shadow of the pyramids, Monge coordinated this immense intellectual project. He established the Institut d'Egypte in Cairo, a learned society modeled on its Parisian counterpart, where the savants presented their findings. They catalogued ancient monuments with unprecedented precision, studied the geology of the Nile Valley, documented unknown species of flora and fauna, and laid the groundwork for the monumental publication, the Description de l'Egypte. Here, Monge was the quintessential savant administrator, blending scientific inquiry with imperial ambition. His personal courage during the campaign became legendary when the French fleet was destroyed at the Battle of the Nile. Stranding the army, he famously declared he would stand and fight alongside the common soldiers, a symbol of the unity between the intellectual and the military arms of the Republic. This profound personal loyalty, forged in the heat of revolutionary fervor and the sands of Egypt, bound him inextricably to the destiny of Napoleon. This allegiance had elevated him to the highest echelons of power and influence. It would also dictate the tragic circumstances of his final years. The unbreakable bond forged between the mathematician and the emperor, an allegiance that had propelled Monge to the apex of French society, made his subsequent fall from power as certain as it was precipitous. With Napoleon's final defeat at Waterloo in 1815 and the ensuing Bourbon Restoration, the political winds reversed with hurricane force. For the new monarchy, every symbol and servant of the Napoleonic era represented a threat to its fragile legitimacy. Monge, the steadfast Bonapartist, the senator of the empire, and the intellectual confidant of the vanquished ruler, became a prime target for political reprisal. His unwavering dedication to the fallen emperor was viewed by the restored regime as an act of profound disloyalty. Consequently, the retribution was swift and absolute. A series of royal decrees systematically dismantled his public life. His titles, his pensions, and all his hard-won honors were rescinded. The final, most wounding blow came in 1816. By royal ordinance, his name was struck from the rolls of the Institut de France, the reconstituted French Academy of Sciences. The very institution he had helped to establish, the intellectual heart of the nation he had served for decades, cast him out. His colleagues, some of whom owed their careers to his patronage, were either powerless to intervene or, in a quiet act of self-preservation, chose to look away. This expulsion was a form of intellectual exile, isolating him from the scientific community he had so profoundly shaped. The man who had organized the scientific plunder of Italy and Egypt, who had directed foundries and educated a generation of France's military and civil engineers, was now an outcast in his own city. His final years were spent in a state of diminished capacity, his health failing under the weight of political persecution and personal sorrow. He lived in relative obscurity, a ghost of the revolutionary and imperial past, haunting the boulevards of a Paris that was trying to forget him. When he died in 1818, the government forbade the students of his beloved École Polytechnique from attending the funeral. In a final poignant act of defiance, they disobeyed, marching in procession to the cemetery to pay their last respects to their intellectual father. It was a gesture that affirmed the enduring power of his ideas, a legacy that political decree could tarnish but never erase. The circumstances of his end serve as a stark illustration of the perilous compact between scientific genius and state power, where the tides of political fortune can elevate a thinker to unprecedented heights of influence before leaving him stranded by the shore. To assess the legacy of Gaspard Monge is to trace the hidden architecture of the modern world. His contributions extend far beyond the confines of pure mathematics, becoming embedded in the very logic of how we design, build, and perceive our physical reality. His life's work represents a grand synthesis, a unification of abstract thought with tangible creation. The invention of descriptive geometry was his foundational act. Before Monge, the representation of complex three-dimensional objects was an artisanal skill, reliant on intuition, trade secrets, and cumbersome physical models. He provided a universal, rigorous, and teachable system. The method of projecting an object onto orthogonal planes, the plan, the elevation, the profile, was a revolution in visual information. This geometric language, which rendered three-dimensional forms onto two-dimensional planes with absolute precision, became the foundational grammar for the industrial age. Every engineering blueprint, every architectural drawing, every mechanical design that has been drafted from the 19th century onward carries within its intersecting lines the echo of Monge's insight. He gave engineers and architects a way to think on paper, to solve complex spatial problems of clearance, intersection, and construction before a single piece of stone was cut or a single plate of iron was forged. His explorations into the differential geometry of surfaces opened another vast frontier. By applying the tools of calculus to the study of curves and surfaces, he initiated a field that would become central to physics and engineering. His work on lines of curvature, the characteristic strip, and the properties of developable surfaces provided the mathematical vocabulary for describing everything from the hull of a ship to the geodesic domes of the future. These concepts, further developed by his students and intellectual descendants like Gauss and Riemann, would eventually underpin the mathematics of Einstein's general relativity, where the geometry of space-time itself is curved. Monge's initial investigations into the local properties of surfaces became the seed from which our modern understanding of geometric manifolds grew. His impact, however, was institutional as well as intellectual. The École Polytechnique stands as perhaps his most enduring monument. It was the physical embodiment of his pedagogical philosophy, a radical fusion of high-level theoretical science with practical hands-on application. This model, conceived in the crucible of revolution to produce a new elite of Republican leaders, became the global template for technical education. Universities from West Point in the United States to the great technical institutes of Germany and beyond adopted its structure and its spirit. Through the École Polytechnique, Monge has created a self-replicating system for innovation, seeding entire generations of engineers, scientists, and administrators who would build the infrastructure of the modern state, its bridges, its canals, its railways, and its industries. He personified the Enlightenment ideal of the savant, a figure for whom knowledge was a unified whole, indivisible from public service and civic duty. His mind moved seamlessly from the abstract curvature of a surface to the optimal casting of a canon, from the organization of a national curriculum to the cataloging of an Egyptian artifact. He saw mathematics as a tool for human progress, a means to rationalize production, to strengthen the nation, and to elevate the human condition. His life demonstrates with extraordinary clarity how a single powerful geometric idea, when placed in the hands of a brilliant and determined individual at a pivotal moment in history, can permanently reshape the intellectual and material world. His name may lack the immediate recognition of a Newton or an Euler, yet his vision is written into the very structure of our civilization, in the logical elegance of a blueprint, the algorithmic heart of a computer-aided design program, and the enduring promise of a technical education that unites theory with practice. Gaspard Monge taught the world a new way to see, and in doing so, he gave it a new way to build. We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.